All right, this lecture will be focusing on the Poisson process, specifically as it manifests on the half line, often representing time. Let's just start by defining simple point processes on the half line more formally. A stochastic process n, which maps from our sample space omega to the set of non-negative integers z plus, indexed by the non-negative reals r plus, representing time, is called a counting process if it satisfies two conditions. First, n not n at time 0 must be 0. Second, for every outcome omega in omega, the sample path n of omega, which is a function from r plus to z plus, must be non-decreasing, integer valued, and a right continuous function of time t. Each discontinuity in the sample path of such a counting process can be visualized as a jump. A simple counting process, which is what we're typically interested in with Poisson processes, has the property that its jump sizes are almost surely unity. It's worth noting that general point processes in higher dimensions don't always have this straightforward inter-arrival time interpretation that we get on the half line. You can see an example of a sample path of a simple counting process in the figure. It starts at 0 and at certain points in time it jumps up by 1. The points where these discontinuities or jumps occur are called the arrival instants of the counting process n. The nth arrival instant is a random variable which will denote as Sn tilde, mapping from omega to r plus. It's defined inductively. S naught tilde is defined as 0. For n in the set of natural numbers, Sn tilde is the infimum of the set of all times t greater than or equal to 0, such that nt is greater than or equal to n. From these arrival instants, we can define the inter-arrival times. The inter-arrival time between the n-1 thea and nth arrival is denoted by xn, and it's simply Sn tilde minus S tilde sub n minus 1. A quick reminder, for a simple point process, the probability that any inter-arrival time xn is 0 or less than or equal to 0 is 0. This just means we don't have simultaneous arrivals. We have an important lemma that connects the counting process n and the arrival process S tilde. It states that these two processes are, in a sense, inverses of each other. Specifically, the event that Sn tilde is less than or equal to t is equivalent to the event that nt is greater than or equal to n. Let's briefly look at the proof. If an outcome omega is in the set where Sn tilde is less than or equal to t, then by definition of S tilde sub n, n at time Sn tilde n sub S tilde n must be n. Since n is a non-decreasing process, it follows that nt must be greater than or equal to n sub S tilde n, which is n. Conversely, if omega is in the set where nt is greater than or equal to n, then by the definition of Sn tilde as the infimum time to reach n counts, it directly follows that Sn tilde must be less than or equal to t. As a corollary to this, for the arrival instants S tilde associated with the counting process n, we have that the event Sn tilde is less than or equal to t and Sn plus 1 tilde is greater than t is equivalent to the event nt equals n. This holds for all non-negative integers n and all non-negative times t. The proof is straightforward. The event Sn plus 1 tilde is greater than t is the complement of Sn plus 1 tilde is less than or equal to T. Using our previous lemma, this is the complement of Nt is greater than or equal to n plus 1, which is simply Nt is less than n plus 1. Therefore, the event Nt equals n can be written as Nt is greater than or equal to n and Nt is less than n plus 1, which using the lemma again translates to Sn tilde is less than or equal to T and Sn plus 1 tilde is greater than T. Here is another lemma connecting the distribution of arrival times to the probability mass function of the counts. Let Fn of x be the distribution function for the nth arrival time, Sn here. Sn denotes S tilde n. Then Pn of t, which is defined as the probability that Nt equals n, probability Nt equals n, is equal to Fn of t minus Fn plus 1 of t. The proof of this involves observing that the event Sn tilde is less than or equal to T can be expressed as the union of two disjoint events. First, Sn tilde is less than or equal to T and Sn plus 1 tilde is greater than T, which is Nt equals n. And second, Sn tilde is less than or equal to T and Sn plus 1 tilde is less than or equal. Now let's move to a characterization involving IID, exponential inter-arrival times. A proposition states that the counting process n associated with a simple Poisson point process S on the half line is a Markov process. For the proof, let's define the filtration script F sub t as the sigma algebra generated by ns for all s less than or equal to t. This represents the history of the process up to time. Then, due to the independent increment property of Poisson processes for any historical event Hs, in script F sub s, the probability that Nt equals n given Hs intersected with ns equals k is simply the probability that Nt minus ns equals n minus k given Hs intersected with ns equals k. Because of the independent increments, this simplifies to the probability that Nt equals n given ns equals k. The transition probability matrix P of St would have its k nth entry given by e to the power minus lambda of interval open from S to t, closed times lambda of interval from S to t, closed raised to the n minus k over n minus k factorial for n greater than or equal to k and 0 otherwise. As a reminder, a Markov process X is time homogeneous if its transition matrix P of St depends only on the difference T minus S, i.e. P of St equals P of T minus S. Thus, the counting process for a homogeneous Poisson point process is a time homogeneous Markov process. In this case, the knth each entry of the transition probability P of St becomes e to the power minus lambda of t minus s times lambda of t minus s raised to the n minus k over n minus k factorial. An important theorem states that the counting process n associated with a simple Poisson point process S on the half line is strongly Markov. Now for a key proposition, a simple counting process, N is associated with a homogeneous Poisson process with a constant intensity, density, lambda if and only if its sequence of inter-arrival times, x mapping from omega to r plus raised to n, are independent and identically distributed, i.e. random variables, each following an exponential distribution with rate lambda. Let's look at the proof. First, assume NT is a counting process for a homogeneous Poisson process on the half line with constant intensity, density, lambda. From one of our earlier equivalences, specifically equivalence 3 from the theorem on equivalences in lecture 24, which states that n of A is Poisson with mean lambda of A, we can determine the distribution of the first inter-arrival time, x1. The probability that x1 is greater than t is the same as the probability that nt equals 0. For a homogeneous process, lambda of interval from 0 to t closed is lambda t. So P of nt equals 0 is e to the power minus lambda t. This is the survival function of an exponential distribution with rate lambda. So x1 is exponential with rate lambda. Continuing the proof, it suffices to show that the entire sequence of inter-arrival times x is IID. We know n is a Markov process, and in fact, it has the strong Markov property. The sequence of ordered arrival points, S tilde, is a sequence of stopping times for this counting process, n. From the strong Markov property, it follows that the process n sub s tilde n plus t minus n sub s tilde n for t greater than or equal to 0 is independent of the history up to s tilde n sigma algebra of ns for s lesser than or equal to s tilde n, and therefore independent of s tilde n itself and n sub s tilde n. Further, we see that the n plus 1th year inter-arrival time, xn plus 1, is the infimum of t greater than 0, such that n sub s tilde n plus t minus n sub s tilde n equals 1. It follows from the independence provided by the strong Markov property that this sequence x is an independent sequence. For a homogeneous Poisson point process, the process n sub s tilde n plus t minus n sub s tilde n has the same distribution as nt due to stationary increments of the homogeneous Poisson process. Hence, xn plus 1 will have the same distribution as x1 for every n, establishing that they are identically distributed. For the converse part of the proof, given an IID sequence of inter-arrival times x, where each xi is exponentially distributed with rate lambda, we define the nth arrival instant Sn tilde as the sum from I equals 1 to n of xi. Then the number of arrivals in the time duration from 0 to t, nt, is defined as the sum over n in natural numbers of the indicator that Sn tilde is less than or equal to t. It's clear that nt constructed this way is pathwise non-decreasing, integer valued, right continuous, and simple, since the probability that x1 is less than or equal to 0 is 0 for an exponential distribution. Therefore, n is a simple counting process. For this process, the probability that nt equals 0 is the same as the probability that x1 is greater than t, which for an exponential distribution is e to the power minus lambda t. It follows that the void probabilities are exponential. From our equivalence 2 in the theorem on equivalences lecture 24, stating that exponential void probabilities imply n of A is Poisson. The random variable nt is Poisson with parameter lambda t for all t in R plus. Therefore, n is a counting process associated with a homogeneous Poisson process with constant intensity density lambda.
For many proofs regarding Poisson processes, it's useful to partition this sample space based on the number of arrivals in a given time, that is using the disjoint events nt equals n for n in z plus. To do this legitimately, we need the number of points in any finite interval to be almost surely finite.
This is captured in the following lemma. For any finite time t greater than 0, the number of points in the interval open from 0 to t closed from a Poisson process is finite, almost surely. The proof relies on the strong law of large numbers. We know that Sn tilde over n the nth arrival time divided by n converges almost surely to the expectation of x1, which for an exponential with rate lambda is 1 over lambda. Now, fix some t greater than 0. Let m be the set of outcomes omega in omega for which n of omega t is infinite. If an outcome omega is in M, it means Sn tilde of omega is less than or equal to t for all natural numbers n. This would imply that the limit superior of Sn tilde over n is 0. But this contradicts the strong law of large numbers, which states the limit is 1 by lambda, a positive constant. Therefore, the set M must have probability measure 0.
Next, let's look at some distribution functions related to the arrival process. A lemma states the following are true for the n at the arrival instant Sn tilde of a Poisson arrival process. S tilde from omega to r plus raised to n with a constant intensity density lambda.
A, the moment generating function of S tilde sub n, m sub S tilde n of theta, which is the expectation of e to the power theta S tilde n, is lambda to the n divided by lambda minus theta to the n times the indicator that theta is less than lambda plus infinity times the indicator that theta is greater than or equal to lambda. B, the distribution function fn of t, which is the probability that Sn tilde is less than or equal to t, is 1 minus e to the power minus lambda t times the sum from k equals 0 to n minus 1 of lambda t to the k over k factorial. This is the CDF of an Erlang or gamma distribution.
C, the density function fn of s is that of a gamma distribution with parameters n and lambda. That is fn of s equals lambda times lambda s to the n minus 1 over n minus 1 factorial times e to the power minus lambda s.
Now, a corollary concerning the counting process n associated with this Poisson arrival process S tilde having constant intensity density lambda, the following statements are true. A, the relationship between the distribution of the nth arrival instant and the probability mass function for the counting process is given by fn of t equals the sum for j greater than or equal to n of p, j of t, where pj of t equals p of nt equals j. B, For each t in R plus, the probability mass function P sub n, an element of script m of z plus for the discrete random variable nt is given by Pn of t, which is the probability that nt equals n equals e to the power minus lambda t times lambda t to the n over n factorial. C. The relationship between the distribution of the nth arrival instant and the mean of the counting process is given by the sum over n in natural numbers of fn of t equals the expectation of nt. D. For each t in R plus, the mean expectation of nt equals lambda t. This directly explains why lambda is called the rate parameter for the Poisson process. Let's briefly look at the proof of this corollary. We use the inverse relationship. The event Sn tilde is less than or equal to t is equivalent to nt is greater than or equal to n. A. The result follows by taking the probability on both sides of this inverse relationship. Fn of t equals the probability that Sn tilde is less than or equal to Tp S tilde n lesser than or equal to t, which is the probability that nt is greater than or equal to np of nt greater than or equal to n. This in turn is the sum for j greater than or equal to n of the probability that nt equals jp of nt equals j, which is the sum for j greater than or equal to n of pj of t. B. This result follows from the explicit form for the distribution of Sn tilde, which is gamma or Erlang, and by recognizing that Pn of t equals Fn of t minus Fn plus 1 of t, as we established earlier. C. This result comes from the observation that the sum over n in natural numbers of Fn of t is the expectation of the sum over n in n of the indicator that nt is greater than or equal to n. This is the sum over n in n of p of nt greater than or equal to n, which is a known identity for the expectation of a non-negative integer valued random variable. So it equals expectation nt. D. This result follows by summing the distribution function of the nth arrivals. Expectation nt is the sum over n in n of fn of t. Substituting the form of fn of t and performing the summation, which involves recognizing series expansions related to the exponential function, we find it simplifies to lambda t. For example, sum for n in n of 1 e to power of minus lambda t times sum over k equals 0 to n minus 1 of lambda t to the power k by k factorial simplifies to lambda t. As a final reminder, a Poisson process itself is not a stationary process. This means its finite dimensional distributions are not shift invariant. This is quite clear even by just looking at the first moment. The expectation of nt is lambda t, which is linearly increasing in time, clearly not constant or dependent only on the length of an interval if we shift the starting point. This concludes our detailed look at the Poisson process on the half line.